flowing to the handcuff to the main character, and maybe the air gap if the two men aren't touching, and to the suspect, to the handcuffs, and back to the power line. And
okay, can you show the video again? I want to see that. So please explain.
Oh, so in this part, they're electrocuted, electroshocked. But this is physically impossible. So to show why it's impossible, we can use Ohm's law to see how much current is flowing through the two men. And we know that the voltage difference is 0 because they are touching the same point on the power line. And let's assume the total resistance of their bodies is 2000 omega. So the current would be 0 ampere.
Yes.
Yeah, so in this scenario, no current is flowing through their bodies.
Okay.
And let's look at another scenario where the circuit is between a man and the ground. So the proposed path would be from the power line to the handcuff to the main character and through the air gap to the ground.
Okay.
And let's assume the power line the voltage of the power line is 11,000 volts. And we know the required voltage to create a conductive arc is about 30,000 volts per centimeter. So the maximum arc distance is 0.37 centimeters. And this is relatively much smaller than the height of the power line. So the voltage of the power line is insufficient to create an electric arc to the ground in this scenario.
Okay.
Yeah, so we explain why the two men won't have any current flowing through them, but let's see why the handcuff would not heat up and break. So let's overestimate a possible current flowing through them. As we assume a large voltage drop of 0.2 volts across the handcuff, and a low resistance of the handcuffs is 0.01 omega. And by the Ohm's law before, we can know the current flowing through the handcuff would be 20 ampere. And the power of that current dissipated as heat would be 4 watts. And this is approximately the power to light up a small LED bulb, which is which is incapable of heating up a metal handcuff into breaking it. Yeah, so this is another violation in the clip we see. So now let's look at the revised version. Yeah, so the handcuff would not break and the two men would not be electroshocked.
Okay.
Thank you.
Okay. Good, great. So why did you assume 0.2 volt?
Sorry?
Why did you assume 0.2 volt?
Oh. Wait. Oh, because they, in theory, they are at the same voltage, but because like they are connected to the same point of the power line, but for, let's say for a moment that there are a voltage drop, and 0.2 volts is considered a large voltage drop.
So why is it 0.2? That's what I'm asking.
Oh, I'm just picking a random number.
Well, that's not good, right? Can you assume like 10,000 volts, because that's the voltage of the line, right?
But a voltage drop wouldn't be that huge because they are both connected to the metal handcuff.
Okay. Grace, in your report, please assume the hand cap is connected to the ground, and then we calculate this part. Okay. Other than that, it was very good. Thank you, Grace.
Okay.
Okay. Okay, and here is my scenario. Professor, can you hear me?
Who are you?
Oh, I'm Hannah.
Okay.
Okay, and this scene is a... Yes?
What's the problem here?
And this scene is about the main character rides motorcycle with two people, and then they crash through the guardrail and fall into the water. And later,
Okay.
yes, and later the fishermen rescue them by using a fishing net. So, and I think this situation is impossible because that the fishing net couldn't afford their huge weight. So my main question is the fisherman able to pull them from underwater to boats? And I divided into stage 1 and stage 2. Stage 1 is pulling from underwater to the water surface. And stage 2 is pulling from the water surface to the boat.
Okay.
Okay, so I use the official mass of the character is 17 kilogram, and I assume that the mass of motorcycle is 200 kilogram.
Okay.
Okay, so in stage 1 we can calculate the weight is approximately 4,000 Newton, and I use the density of human to calculate the volume of people is 0.07. And I use the density of steel to approximately calculate the volume of motorcycle. So we have the total volume. And use the total volume, we can calculate the buoyant force, which is the density of water times volume times g. So it's 2,300 Newton. So in order to pull this object from underwater to the water surface, the pull force must greater than 1,700 Newton. But we have the maximum human pull strength, which is world record is 500 Newton. So this is quite impossible. And then we move to stage 2. Stage 2 is to pulling, assume that they have been pulled from underwater to the water surface. And now they have to pulling from the water surface to the boat. So again, the weight is same. And when the object is completely out of water, the buoyant force will immediately drop to 0. So the pull force must to completely overcome the weight, which is 4,000 Newton. And is again more impossible since the maximum human pulse rate of that is the world record is 500 Newton. Yes, so my conclusion is the fisherman is not able to pull them to boat. And since the force that he needs to apply is far exceeds the maximum human capacity, especially in stage 2, which is much larger pull force. And also the fishing net strength is insufficient to support the huge load and would definitely break.
Okay, good.
Okay, and I use AI to create a revised video. So the fishing net would break and 3 people and the motorcycle would fall back into the water again. Yes. And here is my part.
Okay, good.
Okay.
So in your report, Hannah, can you calculate which crane can support this 4,000 Newton? And then add it to the report, okay?
What, please?
Crane, machine.
Oh,
if you use a machine,
okay.
what kind of machine you need to pull up these guys?
Okay.
Please add it to the report.
Okay. Thank you, Professor.
Okay.
Okay.
Thanks, Hannah.
Okay, and
also next is Joy.
Yes. And my name is Joy, and this is my video.
Okay. So can you explain what's the problem?
It has 2 problems, and the first question is, can a water rocket fly in a crude path in the sky? And the second question is, can a water rocket fly forward but have its nose cone fly back after the explosion? And
Can you show that part? I didn't see what's the problem. So.
okay.
So this is water rocket?
Sorry. Can you say again?
Explain the program.
Oh, okay. The first question is that the water rocket should follow a parabolic trajectory. The scenario in the video is that after they launch the water rocket, it flew off course in a crude path. But I find...
Go back one step.
Sorry.
Go back one step, please.
Okay.
So the program is it's not following a parabolic path. Is that a problem?
Yes.
And then next program is?
And the next program is after it when it is explosion, it's the tail of the water rocket is the nose cone of the water rocket is facing forward, but after the explosion, the water rocket nose cone fly come back, so it is wrong.
Okay. Well, it's better to present the second slide first, program first, then video. Otherwise, people don't understand what's the program. That's what I say every week. Okay, go ahead.
Okay. A scenario in the video is that the nose cone was facing forward at the moment of the explosion, but after explosion, the nose cone fly back.
So what happened to program 1? Program 1, you skipped. You have program 2 on the slide. Are you going to start from program 2? What about program 1?
This?
Yeah, you skipped this.
Oh, okay. I find a theorem about the projectile motion is the trajectory followed by the object would be a parabola in the absence of external forces when it is flying in the sky. And the projectile motion, we can see these graphs, and an object fly with velocity v, and the start angle is theta, and the horizontal position I call it r, and the vertical position I call it h, and vx is the velocity parallel to x-axis, and Vy is the velocity parallel to y-axis. So Vx is equals to V times cosine theta, and Vy is equals to V times sine theta. And the total time equals is 2 times Vy divided by g, because when the object fly half of the routine, it will cause the time is Vy divided by g, so the total time is 2Vy divided by g. And the horizontal position r is equals to Vx times t, because Vx is absence of external forces, so when it is flying, the Vx won't change, so the horizontal position is Vx times t. And the vertical position h is equals to Vy times t half minus g half and t half squared. Because it should minus the half g times t half squared is because use the triangle.
That's fine. This is okay. This is good. Let's go to the next slide.
Okay, so I use this theorem and just is that just in the video the water rocket fly could pass, but it should be a parabola. So I find this is the problem.
Okay.
So the violation 2. The theorem about the conservation of momentum is that if the net force acting on an object is 0, the momentum vector sum of each object in the system remains unchanged, and the center of mass of the system retains its original state of motion. And this picture is I want to show when its explosion, the North Cone was facing forward, but after the explosion, the North Cone come back. So
that's fine. Okay. This is okay. Next slide, please.
Conservation of momentum is talk about the sum of initial p should equals to the sum of.
Fine. Everybody knows that. So can you go to the next? Next slide, please.
So I create this video, and I want to show is that when the scenario in the video, it's the North Cone come back only will occurs when the North Cone and the tail of the water rocket looks at the same, it will happen. So I think it is wrong.
Okay, good. Good, Joy. Very interesting problem. So I have two comments. The first one, you assume there's no external force, right?
Yes.
But because it was not in parabolic orbit, so there was external force. So can you calculate how much force is needed? Say if it's maybe tornado. Let's assume tornado. What kind of tornado is needed? How big tornado is needed to change the orbit? Okay, that's first comment.
Okay.
The second one, please, to make it come back, what is needed? First, you need some explosions to make it separate, right? And
yes.
How big the explosion is needed? Please calculate. Okay.
Okay.
So these two, please consider in the report.
Okay.
Okay. Thank you, Joy.
Thank you.
Good. Next.
Hello, I'm Xiao Yisheng. English name is Yisheng, and in this video, is my original video.
Please explain the problem.
Oh, but because like Kanji's level work is like very so fast, and the wind he invoked make the man in the video you can see like spin. Yeah, I think it's possible. So I next few page I will show you why the speed is impossible.
Good.
So my question is how fast for the wind he create to make the old man spin. I will use two stages to calculate. First one, I will calculate by angular momentum, and the second, I will use the wind or force to calculate the speed. And I will make some assumption about mass and the inertia. I assumption the man is like 60 kilogram, and he spin like 5 reps now 9 seconds. And I assume the spin is a solid cylinder system. So the inertia of the man is after calculation is 1.9, and yes, this is the solid cylinder formula for calculate for the man. And the first one, I want to calculate the biangular momentum, and because he spin 9 revolution 5 seconds, so the angular velocity is about 11.3 radian per second, and we can calculate by I omega is L equals I omega equals 1.9 times 11.3, and we can get the 21.
Mm-hmm.
And I want to use the force of wind to calculate the bike speed, and I choose the formula above is this is 1 divided 2 times low times drag coefficient for side facing person, and times A is the side area of the body, and times the square of bicycle speed. And the force as a arm revolution is giving the man a torque to make the man spin. So I make the assumption of the arm is 0.25 meters, and the strong wind act only while the bicycle and it weight beside the person. So if the effect length of the region is 2 meters, then the interaction time is like delta t approximately equals to LEFF divide V. And I use the formula to calculate the first one formula to calculate the V, and I substitute the formula I mentioned before. I substitute the wind of force and the torque, and we can get the second formula. I omega equals to 1 divided to rho C D A R EFF L EFF V, and after expansion, not expansion, I substitute, we can get this formula, and we just need to fill in the numbers. We can get the speed of the kanji, and after calculation, I think it is possible, and it's not reasonable, because he need to ride to at least 360 km per hour, and I neglect some like friction and some environmental factor. So I think it's the least speed for him to ride. My part is over. Thank you.
Okay, you're Isong, right?
Yeah.
I don't understand why you calculate the momentum of a bike, because bike is going straight, right?
Yeah. Because
there's no angular momentum.
because I assumption like oh no it's the mass angular momentum. I make a mistake. It's the mass angular momentum.
And then, so where did you get this 360 kilometer per hour?
Per hours.
Yeah.
This I use this invention and the substitute, and we can get a v. We use the delta of angular momentum of the man, and we substitute the F wind and the torque, and we can get a v.
What's the delta L here?
Delta L is the change of the man's momentum. Is this? L is the mass of momentum. I think it's a steady. The force is a steady force. And the impulse force, so the force is a steady one. So I think it's the consistent. What's that? A consistent system.
So I estimate. So what is n here? N. What is n here?
N is the revolution. The main spin after the observation I think is the 9 revolution per 5 seconds.
That's what you mean. Okay.
Yeah.
Okay, and then next, please.
Yeah.
Okay, and then next. So, and then how the bike give the people this momentum? Angular momentum?
The wind invoked by the bike.
Okay.
Yeah.
And then this F wind, how did you calculate this F wind?
F wind is this.
This is what you're doing.
Yeah.
Okay.
So the wind invoked by the bicycle, like give the man
Okay,
a
next
torque.
page, next slide. Next. And then you put numbers in, and then you get the velocity. Okay. Okay, this is good. Okay. But you said the bike angular momentum, so it was difficult to follow. But Ison, so your angular momentum is too large. So just to make them move a little bit, what kind of speed is possible? Can you recalculate this in your report, please?
Okay.
Okay. Thank you very much.
Thank you.
It was very good, except that you said bike momentum.
Sorry.
It's okay, but it was good.
Thank you.
Okay. Thank you, Joy. I like that. Not Joy. Ethan. Who's next?
Hello. Good morning. My name is Scott. Hello.
Yeah, go ahead.
Okay.
Got it.
This is my video.
Please start from the question. Start with the questions.
This question is, he made a right angle turn at a speed of 19 kilometers per hour, and he didn't crash. It is possible complete the action in the video, and what condition or change点 do I need? And that's how to calculate the upturn.
Okay, let's watch the video.
Okay.
Explain.
He rise so fast and wait. Here he made a right angle turn, and it is impossible.
Okay, good. So far, good.
Okay, and I think some solution and feasibility. And first, he can change his bicycle, but he very poor, so this is difficult. And second, he can choose a better road, because the North Force can provide a portion of the centripetal force. And I list some knowledge and calculations before solving the problem. And first, I need to know the definition of curvature and radius of curvature, and make this problem easier. And static Fission's formula, and confine that the radius of curvature of the circle is fixed, and coefficient the static friction of S4 rod in Japan, mu s equal 0.9, and centripetal force in calcular motion formula. Wait for me. And this is my calculation. And we define a curvature K first. And K equal d theta over ds.
So you only have 2 minutes to go, so please summarize. You don't have no time to go through all this.
Sorry.
Please summarize, because you don't have time to know all of the details.
Look at here. We can know it is possible to make a right angle turn, and radius of curvature of a circle is radius. And make some calculation. We can know he may be on a slab with 31.6
What's the radius?
radius. My radius is 100 meter.
Huh? You need a
Here.
meter radius to turn 90 degrees?
I suppose the radius is 100 meters.
But it's just one corner, right? So it's probably a few meters long, right?
Yeah.
And what did you assume for the speed?
His speed is 90 kilometers per hour.
Okay, but that's too fast for bicycle, no?
Yeah, because.
But anyway, go ahead. Please summarize.
Okay, so I calculate what angle he can make a safe turn. So I get 31.6 degree.
Okay, did you finish?
Yeah.
Okay, so this is good. This is very good. What's the name? Scott.
Yeah.
But can you assume more realistic conditions? So 90 kilometer per hour is too fast.
But he said
30 or 40 kilometer per hour. That's a more realistic speed for the fast bicycle. Okay, and 100 meter of radius is too large. If you in one corner of a road, it's probably maybe 10 meter max, no?
Oh, okay.
Yeah, so please assume these more realistic numbers and then see what angle is needed. Okay?
Okay.
Other than that, it was very good.
Oh,
Okay.
thank you.
Hello, my name is Lily. And
Lily?
Yes, Lily. And this is the original fragment I chose. This is
Yeah.
Okay, this is the flying food delivery, and I think it is a creative and smart way, but here are some questions after I watch the video. First one is, can a hot air balloon carry that much weight? And the second one is, can a balloon stay still at a specific floor level? And the last one is, can you also use a suction cup to attach the balloon to a building like the picture shows? So to know the answer of the first question, we need to calculate the buoyancy of the hot air balloon and the estimated mass that it can lift. So I assume the volume of the balloon is a common size and is 2,500 cubic meter. And the density difference of hot and cold air is 0.2 kilogram per cubic meter. And by the formula of the buoyancy, we can know the hot air balloon can lift a weight of 500 kilogram. And we know that the full balloon system is about 400 kilograms, concluding the envelope, burner, and the basket. And the load is about 340 kilograms, concluding 2 adults and the goods. So the total mass is about 740 kilograms, which is much heavier than it can support. So it is hard for them to sell goods and even cook ramen in the air. And the second question is, can a balloon stay still at a specific floor level? We know that the hot air balloon can only control the vertical motion by heating or cooling the air in the balloon. So even a small change in temperature can cause acceleration. It makes it difficult for them to maintain a constant altitude at a given floor. Now let's see the first formula. The roll out means the density of cool air outside of the balloon, which is bigger than the roll in. So by this formula, we can calculate the balloon's net force. And also, all the horizontal motion depends on the wind's direction. So under a moderate wind speed, the hot air balloon drifts 5 meters per second every second. So, and to maintain in a 1 to 2 meter windows. The timing need to be controlled in 0.2 to 0.25 seconds. It is difficult for their delivery. And the last one is, can NTHU use a suction cup to attach the balloon to a building? First, we need to know the total force on the suction cup. As the first question, we assume the mass of full balloon system is about 400 kilograms, and the wind speed is 10 meters per second. So we can calculate the total force is 4,300 newtons. Next, we want to know whether a suction cup can stand this force. So I assume the diameter of it is 15 centimeters, and max possible pressure difference is 10,000 Pascal. So I can calculate the area and the force on the suction cup. The real suction force, F equals 0.6. F ideal means the 0.6 ideal means the real one instead of under an ideal circumstances. So overall, if NTHU wants to close to a building, he needs at least 4 to 5 suction cups. So let's see the revised video.
Okay.
And also limited to my poor video editing ability. I can't make a perfect video, but what I want to express is the hot air balloon cannot fly stably like the original one and even control its direction easily. So this is my presentation.
Okay, very good, Lily. Can you go back to the first point? The balloon doesn't fly. So what did you assume for the volume of the balloon? It's 2,500. How did you assume? Because if you can make balloon larger, and then it's going to be more floating, right?
Oh yes. I searched for some informations. No.
Okay, Lily. So please calculate in your report how large balloon needs to be, and then is it possible to make such a large balloon? Okay, because it's a little bit, right? 500 and then 740, so just a little bit more, no? Also, you can consider making the air a little bit hotter, and you get more buoyancy.
Okay.
And then second point, please.
Okay.
What was the second point? Oh, the wind?
Yes.
This is very difficult. I don't know how to. So, when people fly the air balloon, how do they control the horizontal motion?
They often have the rope connected to the floor, so it won't fly. Fully depends on the wind.
Okay. Let's go to the third point.
Okay.
So here, assuming the balloon is floating enough, you don't, suction cup doesn't need to hold the weight, right? So if it's just the wind force, then it's maybe two of them is okay, no?
Oh, okay.
That's just a comment. Okay.
Thank you.
So please, in the report, please consider the first point a little bit more, and then it's great.
Thank you.
Your presentation was very good.
Thank you.
Very good, lady. Next, please. Is it Wendy?
Yes. Hello, I'm Wendy. So I'll introduce the anime I chose first, and then I'll analyze why it is impossible, and in the end, I'll show you the revised video. So in this episode, there is a powerful time bomb with 500-meter explosion radius, and is going to explode in 5 minutes. So to reduce the damage, Rozu decided to grab a bicycle and climb the wall of Tokyo Skytree, which is 634 meters tall. So let's take a look at the original video first.
Okay. Can you start from the question?
Okay, so in this video, will see that he's climbing straight upward while accelerating, but it is really possible to ride a bike vertically up to the sky tree. So to figure out the problem, we need to ask two things. First, can Road 2 produce enough power against gravity? And second, can he even stay on the wall? So this question leads us to two key physical ideas, power and friction. Let's talk about power first. So to ride a bike straight up the skytree, Road 2 must continuously produce enough power to lift himself, the bike, and the bump upward against gravity. So we need to analyze how much power he would need. We know that the skytree is 634 meters tall, and the total mass is 100 kilograms. And the bomb, we know that is going to explode in 5 minutes, which is 300 seconds. So the power defined, so here's our assumptions. So we know that the power defined as work divided by time, and work defined as mass times gravitational acceleration times height. So the work is 621,320 joules, and the power will be 2,071.1 watts. So he will need to sustain over 2,071.1 watts to reach the top of the skytree. But this number is extremely high and far beyond humans' physiological limits. So from the power requirement alone, it is already impossible to complete this climb. Okay, so next we are going to talk about the friction. So to stay on the wall, friction must support his entire weight. We still assume that the total mass is 100 kilograms, and the static friction coefficient is 0.15. So, because the Tokyo Skytree is much taller than Road 2, so we can assume it is vertical. Assume the wall is vertical. So the force pulling him down is gravity. And to stay on the wall, the friction must be at least equal to the gravity, which is 100 times 9.8 is 980 Newton. So this means, this requires the normal force of 6,533.3 newtons. So this means Road 2 must push horizontally against the wall with a force equivalent to the weight of over 650 kilograms of force. So no human can generate this amount of horizontal force, especially while pedaling upward at the same time. So therefore, the climbing motion shown in the anime is physically impossible. So now we know it is physically impossible to ride a bicycle vertically up the skytree. The power need is far beyond humans' ability, and the friction required is something no human can generate. So to show what will happen in the reality, I made a revised version of a video. Let's take a look. So we can see in the revised video, he will, instead of climbing upward, he will fall down at the time he reaches a wall. So, and this is the end of my presentation. Thank you.
Okay, excellent, Wendy. This is very good. Yeah, this is very good. Just one comment. Actually, this problem is discussed before by different groups. So please compare your result to their result and then discuss. It makes sense.
Sorry.
Okay.
Sorry, I don't understand.
This is the second time. Some people reported this problem before, so please compare your report with theirs in your report, okay?
Okay. Thank you.
Other than that, it was excellent. Thank you. Thank you, Wendy. So Jay is gonna be the last person.
Yes.
So please start from the problem. Yeah.
Sorry, let me.
Start from the problem.
So, you see the video, right?
Oh yeah.
So, my question is there enough static friction force between the front bumper of the car and the ground? And maybe the car is going to slip into the river. Yeah.
Okay, so what's the problem? Please explain the problem. I don't understand the problem.
The problem is, I think there is not enough friction force between the front bumper and the ground.
So what's the problem?
The problem? What do you?
Yeah.
What do you mean the?
I don't understand the problem. Why are you thinking about the friction between the bumper and the ground? Why?
Why? Because as seen in the video, their car stopped by the friction between. Yeah, you can see the front wheel is.
Can you show the video?
Yeah. The front wheel left the floor. Yeah, right. Yeah, the front wheel. The four wheels, they all left the floor. Yeah, so.
Can you show?
Yeah. Continue?
I see. Okay.
Okay. So the assumption is that I find the AE86 is look alike the car in the video. So the total length is 4.80 meters. So I assume the X, can you see X is right over here? I assume it's 1.7 meters. And the mass center is in the middle of the car. So, and the edge is 0.5 meters. And the mu s between the tire and asphalt road is usually between 0.5 to 0.9. But in the video, they're on the grass, so mu s should be lower than the 0.5. Okay?
Yeah.
Okay, so I will see point A as a fulcrum, and the clockwise torque is mg times x, and the anti-clockwise torque is ma times h, and a is a hypothetical acceleration. And when the front wheel is about to leave the ground, the normal force applied on the front wheel is equal to 0, which as here, NF equals to 0. So that means at this moment, MA times H have to be bigger than mg times x. So A have to be bigger than 3.4 g. And as for the horizontal force applied to the car, there are Fs, which is the friction force, and Ma. And to brake the car, Fs have to be bigger than Ma. So which means mu s has to be bigger than A, and A have to be bigger than 3.4 g. And that means mu s have to be, there's a wrong over here. It's mu s times g have to be bigger than A. So mu s have to be bigger than 3.4, which is impossible. Because as shown in the previous slide, we can see that mu_s is usually between 0.5 to 0.9 on a normal road. And in the video, it's grass, so it should be, the mu_s should be like 0.2. It's way smaller than 3.4. So it's impossible. And here's the revised video. They're just going to slide into a river. Yeah, and that's it.
Can you go back? It's good, but why is it impossible? So, for example, if you're riding bicycle and then if you break the front wheel, you can turn, right? But why it's not possible with the car?
Because in this situation, the front wheel has no normal force from the ground, so there's no friction force applied on the front wheel.
Why there's no friction? There should be, right?
Because in the situation shown in the video, you can see the front wheel is already left the floor.
Oh, okay, please put it on the floor and then recalculate if that's possible.
Put it on the floor?
Yeah.
I didn't calculate that.
No, in the report, please do that. Okay, thank you very much.
Okay.
Actually, Jay, your report could be interesting one. So, Jayo.
Okay, thank you.
Okay, and then you have quiz?
Quiz, Kahoot.
Yep.
So we should give you the pin?
Yes, we are doing this every week.
Okay. So, 你要开那个码是什么？哦 The pin is 2815204。哎，我还是用这开着，用这开。哦。
So, let's share our screens.
Share the Kahoot on. Yeah. Okay. 这用你的吗？哦。还是你直接用这登你的账号？吗？
Have you guys attended this class before?
Attend once.
Oh, that's not good.
你有网络吗？还是你开 Meet 然后加分享你的？
我连不到网络。
你连不到网络？那你这里可以登你的。
可以。
Okay, in the future, please prepare this before the class starts.
Okay.
Don't
bite.
啊。 怎么样往下？怎么样往下？Sorry。哦，滑鼠。
但是 Google Meet 学这个页的话，
Okay, good.
Sorry.
Okay. 136.
095.
Okay. So, can people online please join? Okay. Let's start.
Now?
Yeah. So Lily, you cannot join because you're in the same team, right?
Yeah.
Group 17 people, you cannot join. Lily, you cannot join.
No.
W is not Wendy, right? Okay, let's start.
Well,
Okay, next.
yeah, okay.
Blue and yellow is the same, no?
Oh, yes.
Okay, good job, Peter. Peter is, I don't know, Peter is in the classroom. Okay. Oh, good job. Please report to TA to get the bonus point. Albert, do you have a question?
Oh, never mind.
Okay. I thought some questions are weird today, no? Can anyone point out what was the weird question? Anyone online or anyone in the classroom? Do you have any comments or questions about questions?
They like the blue and yellow one, and I just the yellow one. Which like two same answers.
Yeah, that's true. That's true.
And then like, oh, never mind.
About the breaking down, there was a question about breaking down, no?
Breaking down.
The seventh one. Not that one. About this one.
This one.
Yeah, this one there are multiple answers, no? Can you put options?
Let me see. Okay. How to? On.
Okay, never mind.
Ah.
Okay. Thank you very much, group 17. I enjoyed the presentation. Some of the presentations are very good, so I like that. Then today I need to go to a NSTC meeting, which already started, so I need to finish it here.
Okay.
Any questions or comments at the end?
No.
Okay. If not, thank you very much again, group 17, and then see you Tuesday next week. Tuesday next week, I should be back in the classroom. Okay, thank you again, and see you next week.